So I think I'll make a start. As I say, my name's Dr. Rodri Jervis. I'm a lecturer here at UCL Chemical Engineering. I actually did my PhD at this department as well in fuel cell materials and fuel cell technology. And that's what I'll be talking about a little bit today. You'll have another talk next week in more depth on fuel cell materials, I believe. And you've already had a talk from Paul Shearing and Alex Retty around energy storage technologies, including batteries and other technologies. Fuel cells are an alternative energy storage technology, and I'll talk a bit today about how they encompass lots of different disciplines and lots of different sort of material challenges as well across multiple length scales. This is a taster lecture, and it's largely content that I deliver in my actual lectures. It's a fourth year lecture course. We've had a question already about when these courses are available. Yeah, it's a fourth year MEng or MSc course, elective course. And I'll just go into a bit of background about the team that we have in UCL Chemical Engineering around electrochemical technology. So as I say, we have a lab called the Electrochemical Innovation Lab. This is led by Professors Dan Brett and Paul Shearing. Some of you might have seen Paul Shearing's talk on exploding batteries earlier in the week, which is always very exciting. There's also three more of us. So there's me, Tom Miller, and Alex Retty, who also gave a talk recently, all working in various different areas of electrochemical technology. So this covers batteries and fuel cells, but also things like supercapacitors, more fundamental electrochemistry. We'll talk a little bit about what's so cool about electrochemistry in a second. We're actually quite a large group as well, so I have to update this slide every time I use it because we keep getting more students and researchers, but we're a group of about 70, possibly 75 people currently, and this reflects actually how hot the topic electrochemical devices and engineering are at the moment. So I mean, we see a lot in the news about battery electric vehicles. There's lots of money being flooded into research into these areas to try and improve the UK's standing in electrochemical technology. So it's a growth area. And it's really an area that is sort of new to more traditional chemical engineering disciplines, I guess. And this is something that's reflected really well in the UCL Chemical Engineering department. We have very large electrochemical section. We're the largest research group in the UK in this sort of area, but it's also reflected in the teaching. So you can see here we've got 5 academics in this area, and we teach these courses on energy systems and sustainability, electrochemical engineering and power systems, which Paul and I share, and then advanced propulsion as well, which Alex Retty teaches. And we're expanding in the near future as well into UCL East with a whole lab devoted to advanced propulsion at the sort of larger scale of things. So really it's quite a growth area, quite new area of chemical engineering. I'll show you today a little bit about how fuel cells are actually a multidisciplinary problem as well. So not just chemical engineering, but lots of other disciplines. So I'll skip onto the intro actually there, and I'll give you a bit of background history of fuel cells, how they work, and what sort of materials and material properties have to come together in order for them to work well. There are many advantages of fuel cell technologies and some disadvantages as well, and we'll compare these in particular to lithium-ion batteries and other types of batteries. And then I'll end with a few examples on fuel cells. Okay. Right, so on that picture there, we've got a sort of a fuel cell system from a Toyota Mirai car, and then we've got some cartoons of how the fuel cell works in a bit more sort of detail at a smaller length scale. Fuel cells are essentially quite simple devices, at least on the surface, and what they're doing is converting chemical energy, so a fuel, into electrical energy. And it does this in a direct way by using something called an electrochemical reaction, which we'll come on to in a second. This means there's no combustion, no moving parts, at least in the working part of the fuel cell. There are sometimes peripheral parts that have fans and blowers and things like that obviously have moving parts. But the fundamental aspect of the fuel cell is a direct combination of fuel and oxygen to give you electrical power directly. This isn't 100% efficient, of course, but the efficiencies are much higher than for example, burning gas and using that to heat water to drive a turbine and then generate electricity that way. So it's this sort of directness that makes them very efficient. And because they are ostensibly quite simple without these moving parts, they can, in theory, be very long lasting and very easy to make. But we'll see actually that it's a lot more complicated than that. There's lots of engineering issues surrounding these fuel cells. Just a quick note, actually, we had a poll at the start of this talk just to see how many people had heard of fuel cells before, and only about 10% haven't. So that's great. I know that they're finding their way onto the school curriculum these days, which is excellent. And I think most people have said they would drive a fuel cell car and they think hydrogen is safe or potentially safe. So we'll come on to that in a little bit as well. Sometimes there's some issues around hydrogen. Anyway, onto the background of fuel cells. They're actually a lot older than you might think. So so they were sort of they were initially discovered or conceptualized at the same time by Schonbein and Sir William Grove, who's a Welsh sort of amateur scientist. And basically, they remained a sort of curiosity for a long time until material advances in the 60s meant that they were practical. I think actually, sorry, that's a typo. That should probably say 1838 rather than 1938. They have many applications as well. So fuel cells can power anything that requires electricity, essentially. So from small things like laptops, mobile phones, all the way up to sort of large power plant size fuel cells that are big enough to support whole communities or whole buildings. Most of the focus for research and perhaps a lot of the interest of fuel cells is around automotive applications, so cars, which we'll talk a lot about today. And there are lots of different types of fuel cells as well, and they're often classified by the type of fuel they use or the type of electrolyte that they use. Okay? So this is what the first fuel cell experiment looked like from William Grove back in the 19th century. Electrolysis was known about then, so this is the splitting of water into its constituent gases of oxygen and hydrogen, and that was done by putting a current through two electrodes and splitting the water into those gases. William Grove realized that you could actually reverse that, and if you collect the gases, hopefully you can see my mouse, if you collect the gases at the top of a test tube here, you have a reservoir of hydrogen and oxygen, and then instead of putting electricity into the system, you then turn that power source off, and the system spontaneously then generates electricity by the electrochemical reactions going on here with the hydrogen and the oxygen. And as I say, this is done on two electrodes, often maybe platinum metal or something more like steel or something like that. And you also have to have what's called an electrolyte in there, and that's a substance that allows charged particles that aren't electrons. So these are ions of, for example, sodium and chlorine. If you dissolve salt into water, you get sodium plus and chlorine minus. That then becomes an electrolyte. So he realized that could happen, and that actually happened in, as I say, the early 19th century, and slightly before the invention of the four-stroke engine, so the combustion engine that drives most of our cars still today. I mean, if you think about the complexity of a combustion engine, you've got to have lots of controlled explosions basically happening many hundred times a second. It's quite a difficult thing to come up with, and ostensibly these fuel cells are quite simple, as I'll show you. For a long time it remained a scientific curiosity until about the 60s when some alkaline fuel cells were developed by Francis Bacon and used in the Apollo space missions as well to provide power while up in space. And then we entered a sort of a region of large industrial growth, actually, and interest in fuel cells, largely driven by companies such as Ballard at an entrepreneurial sort of scale. And we're getting to the point now where actually we've got a whole new industry, a burgeoning industry, one that perhaps hasn't quite reached its potential that people thought it would, and is being perhaps overtaken by the drastic decrease in cost in lithium-ion batteries recently, but nonetheless is still quite relevant, and it stands to be quite important in the future as well. So as I mentioned, there are lots of different types of fuel cells. The basic concept of a fuel cell is to combine a fuel with oxygen and to use that to provide electricity directly in the electrochemical reaction. So you can see there's a long list of different types of fuel cells here. There's ones called direct methanol fuel cells, the proton exchange fuel cell, alkaline fuel cells, molten carbon fuel cells, and solid oxide fuel cells. So obviously the direct methanol fuel cell uses methanol as its fuel. Many of the other ones will use hydrogen. Solid oxide fuel cells actually operate at much higher temperature, up to around 1,000 degrees, and so they're a bit more flexible with the types of fuels they'll use. I'll briefly touch on those at the end, but today I'll mainly focus on the PEM fuel cell, that is the proton exchange membrane fuel cell, or the polymer electrolyte membrane fuel cell, as it's sometimes known as well. And we'll focus on that because it's largely seen as the main potential technology for automotive vehicles. Okay. So we're just going to have to go back to a few basics on electrochemical reactions before we start here. As I say, the fuel cell is based on an electrochemical reaction, on actually two electrochemical reactions. That's because all electrochemical reactions are split into half reactions, okay? So you have an overall reaction, but there are two half reactions occurring at different parts of the system. If you look at the little animations over on the right-hand side here, you've got a sort of a view of what a normal chemical reaction might look like, in this case a nucleophilic substitution reaction. That's where all chemical reactions involve the transfer of electrons between different atoms or molecules. And so for a lot of chemical reactions, this happens on a very short length scale. So when the atoms or molecules come together very closely, that electron transfer happens within that region, okay, and then you form a new product and it goes off somewhere else. In electrochemical reactions, this actually happens on the surface of an electrode. An electrode will be something like a metal or carbon, any conductive surface, and your reactant comes towards the surface of the electrode. The electron transfer happens into the electrode, and then that electron charge can travel through a circuit, and that means that we're separating this charge transport, okay? As I say, in electrochemical reactions, you have two of these half reactions going on. So you have two electrodes, one where oxidation is occurring and one where reduction is occurring, okay? Oxidation is a loss of electrons. So that is this kind of blue diagram here where the electrons are going from the reactant into your electrode. And reduction is a gain of electrons where electrons are coming out of the electrode and going into the reactant, okay? So in an electrochemical reaction, you have these two half reactions going on simultaneously. The electrons that are lost from the oxidation travel around some sort of external circuit and are used in the other half reaction that occurs at the cathode where the reduction is going on, okay? So we have an anode where oxidation is happening and a cathode where reduction is happening. And for electrochemical reactions, you always have to have these two things happening in tandem and they have to be linked. But because we've separated these two half bits of the reaction, it means that we can do really useful things with electrochemical reactions, okay? We can either generate useful electrical current, which is what fuel cells are doing, providing good power, or we can do things in reverse where we put electricity in and we force an electrochemical change in the system. So we talk about that a lot in the lecture course as well, about how we can make useful products such as aluminium or the chloralkali process, for example, which is the reverse of that, sort of electrolytic processes. But I'll talk today about generating electricity from these electrochemical reactions via fuel cells. So this is a kind of view of what a kind of traditional electrochemical cell might look like. As I say, you have two electrodes, the anode and the cathode. They're connected with some sort of electrical connection so that electrons can flow between them. But then you also have to have an electrolyte, which normally is some solution, as I say, some salt dissolved in solution, like an acid, or a salt solution like sodium chloride, sodium hydroxide, something like that. And that allows the ionic current to flow, okay? So you have an electronic current that flows in between the electrodes, and you also have an ionic current flowing to balance that within the cell. And that's the three things that you need, basically. You need your electronic conductivity between your electrode surfaces where the reactions can happen, and you need an electrolyte to conduct the ions as well. So in a fuel cell, these half reactions that we're talking about, often when the fuel cell is powered by hydrogen, we'll talk a bit about why hydrogen is attractive as a fuel, but often we're talking about hydrogen in fuel cells. The overall reaction is to combine hydrogen and oxygen to produce water, okay? So the only byproduct is pure water. And if your hydrogen is made renewably, then it's actually a very green process, okay? And actually quite an efficient process as well because it's a direct combination. As I say, electrochemical reactions are always split into halves. In this case, the two half reactions are shown here, the hydrogen oxidation reaction, or the HOR, and the oxygen reduction reaction, the ORR. And so both of these have to happen simultaneously because the electrons that are produced in the hydrogen oxidation reaction have to be used in the oxygen reduction reaction in order to form water, okay? And it's that flow of these electrons from the anode to the cathode that generates the useful electrical power that we use to power a car or any other thing that a fuel cell could power. There's also an associated voltage with this. All electrochemical half reactions have a voltage, and this is a sort of somewhat arbitrary voltage that's been defined actually quite usefully by the hydrogen oxidation reaction. So this is defined as 0, and it happens that the oxygen reduction reaction is at about 1.2 volts positive of that. Okay, so if we combine those two numbers, we can get an overall cell voltage. That means the starting cell voltage of a fuel cell is around 1.2 volts. Okay. If we used a different fuel, like methanol, for example, this wouldn't be the same voltage, and therefore our cell voltage would be different and lower in the case of methanol. Right, so we've gone from this basic configuration of William Grove's experiment sort of 200 years ago with two flat electrodes. And the current that was produced in these experiments is actually really very low, and that's because there's a very low contact area or low surface area, and actually a large distance between the electrodes as well. Okay, so the electrolyte itself has a resistance associated with it, and you want to minimize that. So to overcome that, there's been a lot of development in fuel cells, obviously over the last few hundred years, and in particular the last 10 years or so as well, mainly centered around making very porous, very high surface area electrodes and very thin electrolytes, and actually moving away from these liquid electrolytes or aqueous-based electrolytes to a solid electrolyte, which is a polymer electrolyte, which we'll talk about in a little bit more detail soon. But there you can see in the picture on the right-hand side there of what a modern fuel cell actually looks like, the working part of a fuel cell. And it's essentially a very thin sheet of plastic, it's quite special plastic, and as I say, we'll talk about it in a second. And on top of that, you've got printed these electrodes. So instead of very flat metal surfaces, you've got electrodes that contain very high surface area metal nanoparticles. And that means that we can get a huge amount more reaction happening per second. And the more reactions you have, the more electrons are given off in these electrochemical reactions. And therefore, the more electrons you have per second, the higher current you have, okay? The higher electrical power. So modern fuel cells look quite different. This is an example of what a fuel cell looks like in the sort of very basic schematic. In the middle, we've got what was actually shown there in that photo, this sort of plastic with the electrodes printed on side of it. That's called a membrane electrode assembly, or an MEA. And that's because the electrolyte in the case of PEM fuel cells is actually one of these polymer membranes. Okay, it's a special polymer that allows protons to travel between it, but obviously doesn't allow electrical conductivity between the two electrodes. On either side of that membrane, you have two electrodes that contain a catalyst, and that's where these half reactions occur, these electrochemical half reactions, the hydrogen oxidation reaction and the oxygen reduction reaction. So we have an anode on this side and a cathode on this side, printed onto our plastic polymer electrolyte, okay? And that is the fundamental working part of a fuel cell. That is what does all of the stuff that the fuel cell needs to do in order to generate electricity. But it's not as simple as just that. We need to have quite a few different things surrounding the working part, this MEA part, in order for a fuel cell to work very, very well and to work as efficiently as possible. And there's a lot of engineering and material science that goes into that. So on the outside of this catalyst layer, we'll often have something called a gas diffusion layer, a GDL, and this is a sort of porous, conductive carbon fiber paper type material that allows the gases to spread evenly over the surface of the catalyst. We then have more coarse gas flow channels to deliver the gas to this GDL, but they're often machined into something called a current collector, which is obviously conductive as well, to allow the electrons to come out of where they react in this catalyst layer out into the external surface. There's a lot of engineering that goes into these materials as well. It has to provide the gases in an even way. It has to help with removal of water. So remember, we're generating water in these reactions, and so that can be problematic. Sometimes we need to remove it. We also need a certain amount of water to remain in the system, because these polymer membranes only work in terms of their ionic conductivity, i.e. as electrolytes, if they're well hydrated. Okay, so we've got this working part of an MEA in the middle, and then we've got various ways of delivering the gases in efficient and even ways to the surface of the reaction surface where the half reactions occur. Okay, and then these electrons go through an external circuit and power something on the outside. This is an animated version of what I've just said there. So you can see the hydrogen splits into protons and electrons. That's the hydrogen oxidation reaction occurring at the anode. The protons can travel through this electrolyte membrane. The electrons can't, and so they go through the external circuit, which is conductive, and everything combines there with oxygen on the cathode to form water, and that water is often removed in the exhaust. Okay, so your exhaust pipe on a fuel cell vehicle is pure water. As I say, there's lots of different material challenges and lots of actually different science that occurs on different length scales in order for this to happen. Okay, so the very coarse length scale, we've got flow channels of about 1 millimeter here in the current collectors, and that supplies the gas. Then we're going down to sort of length scales of 150 micron thick gas diffusion layers with fibers that are about 10 to 15 microns in size. Then the catalyst layer has very small particles of carbon on it, around 100 to 300 nanometers, and they have even smaller metallic nanoparticles of catalyst on there, which will be less than 10 nanometers and actually less than 5 nanometers in most cases in terms of modern catalysts. Then we have this polymer electrolyte, which is it's based on Teflon, actually, on non-stick PTFE backbone, but it has special side chain molecules that allow the transport of these charged protons through the electrolyte, and that's quite a thin layer, again, probably 50 micrometers, maybe a bit less in modern membranes, and that there's quite a lot of polymer science and chemistry that goes into that material. And then you have the same sort of thing mirrored on the other side of the fuel cell, where the oxygen is delivered through the same materials. Often these catalysts are quite similar, based on platinum metals. I'll come on to that in a second. So as I say, there's many components that need to come together to make a fuel cell work. These are some of the main ones. So I've mentioned this membrane, which is actually acting as our electrolyte. You can see on the top of the chemical structure here, this is PTFE, which is Teflon. And you've got these side chain molecules here, and at the end you've got this sulfonic acid group, which is charged, and that allows the movement of the protons, the positively charged protons, throughout the structure of this electrolyte. Okay, so some of the benefits of moving towards these solid polymer electrolytes is that you don't get any leaking of fluids. You can move to very thin electrolytes, and so you can stack lots of fuel cells together in a smaller space, and it just makes everything more dense and more efficient. The electrodes then contain a catalyst, and this is a very high resolution electron microscope view of the catalyst. You can see here the light grey balls are carbon, and the dark grey smaller balls on top of them are the catalyst materials. As I say, is normally a metal such as platinum or an alloy. The catalyst layer and the membrane are sandwiched together under heat to make this membrane electrode assembly, the MEA. As I say, that's the working part of the fuel cell. That's where all the chemistry happens to generate the electricity. And then surrounding that, we have these gas diffusion layers, the carbon fiber layers, and current collectors with various different designs of flow fields on them to allow the gases to flow evenly across them. Here's a picture of what a large MEA might look like on the bottom. They look very simple, and they look, quite frankly, quite boring really, but there's a lot of incredible science and engineering that goes into making those things work. As I say, they don't have any moving parts or anything, so all you have to do is supply gas supply hydrogen gas to one side and oxygen gas to the other side, and connect them with a circuit, and you will generate electricity. Okay, it's as simple as that. Obviously, it's a bit more complicated. And there's lots of when we delve in a bit more detail, there's lots of multi-scale problems within fuel cells and within the materials for fuel cells. On the right is a cross-section electron microscopy view of this MEA, this membrane electrode assembly layer. So in the middle we've got this Nafion membrane, that's the polymer electrolyte. And then on either side we have catalyst layers. So this one actually uses a platinum catalyst on the cathode side, and a non-platinum catalyst on the other side, which is where a lot of research is going into at the moment, and trying to reduce the amount of platinum in these systems. And then you can see the gas diffusion layer here, this network of carbon fibers that allows the gas to diffuse evenly onto the catalyst layer. And it actually helps with water removal as well, so that's another big aspect of how these materials work. So there's lots of different desirable properties in these materials, and this is something that I think Theo will go into in much more detail next week in his talk. But broadly, for our membrane, we need it to conduct protons very well, but also be a good barrier to electron conduction. Otherwise, you get a short circuit in your fuel cell. It needs to be impermeable to gases. So if hydrogen can flow through it onto the other side, then we get a sort of chemical short circuit as well, which is not good. So it needs to keep the gases and the electrons out of both sides of the fuel cell. And it also needs to have good mechanical mechanical and chemical stability so that it doesn't degrade over time. The gas diffusion layer needs to be electrically conductive and be porous to give an even distribution of gases, as I mentioned many times. It's often coated in something hydrophobic like PTFE as well to help with removal of water. So when you generate lots of water, when these fuel cells have been operating for a long time, you need to get rid of that water, sorry. So often on top of that, there'll be a carbon ink as well to stop the catalyst just getting lost in these larger pores of the gas diffusion layer. So we have a thin layer of just carbon, and then on top of that, a thin layer of carbon and catalyst layer. And it's the catalyst that actually really helps these reactions, this hydrogen oxidation reaction and the oxygen reduction reaction. It helps those reactions occur at a much faster rate and at a much more useful rate than it would otherwise if you didn't have any catalyst surface there. Okay, so it lowers the energy barrier for these reactions to happen and therefore makes them happen more easily and more quickly. Outside of all of that, you have a current collector which has to be electrically conductive, obviously, and often has to be machinable as well, so that we can put these flow field designs, which hopefully you can see in there, into the current collectors. They're often based on graphite or some sort of graphite polymer composites, or increasingly now actually based on metals. Metals sometimes can corrode in these situations, so you often need to put some sort of corrosion protection onto them. But you can make much thinner current collectors with using metals. So most manufacturers have moved towards metal current collectors now. Okay, so all of these material properties work together to give you a good or hopefully not, but bad performance in a fuel cell. Okay, so we talked about earlier the sort of inherent electrochemical voltage that is given by these fuel cell reactions, and that's about 1.2 volts. Okay, in reality, operating fuel cells never actually achieve this voltage, which we call the open circuit voltage. And that's for various different reasons. One of the main reasons is when you're operating a fuel cell, i.e. you're drawing useful current density out of it. As you do that, the voltage of the fuel cell actually drops off from its sort of open circuit potential. And there's many different reasons for that. And these are called losses in the fuel cell, or polarization losses, okay? And so sometimes you'll see this performance curve of a fuel cell, which is just voltage versus current density. That's sometimes called a polarization curve, okay? So as we work the fuel cell harder, as we take more and more current off the fuel cell, i.e. we power something bigger, or we put our foot down in a fuel cell car, for example, we actually end up losing voltage. And that manifests itself as an efficiency loss in the fuel cell, okay? So if we were getting 1.23 volts out of our fuel cell, that would be 100% efficient. And if we're getting 0.6 volts out, then that's about 50% efficient, okay? As I say, these happen for various different reasons, and various different material properties contribute to these losses, okay? And these material properties have different effects depending on the current density. So the first one to talk about is the what's called the activation losses, and this is driven largely by the catalyst. So the catalysts help lower the activation energy of these reactions, and the better the catalyst is, the lower the loss you get in this region from this activation energy. Okay. As we go into more sort of moderate currents, we actually get a sort of normal ohmic voltage loss. So this is just sort of normal V equals IR type resistance. And that comes from electrical resistance within the fuel cell, the current collectors, the wires, etc. But most importantly, actually, is the ionic resistance of the membrane. So how easily does that membrane pass the protons through its structure? And so having a good membrane, a thin membrane, and actually a well-hydrated membrane is key to lower these losses. As we get into higher current densities, we're driving these reactions even harder, and we're generating a lot more water, and we're also requiring a lot more reactant to get to the surface in order to satisfy the rate of reaction that we need to produce this kind of current. Okay, and so if we're unable to do that, then you actually start to get drastic drop off in the voltage, and that could be due to flooding with water in the structure of these GDLs, and also the current collector bipolar plates. We could get droplets of water blocking the channels there, so we're not getting enough reactant at the electrode surface. So all of these properties need to be taken into account in order to minimize all of these losses and get a more efficient and better performing fuel cell. Okay, so lots of different material properties required to work in tandem there. If we look in a bit more detail about the activation losses, as I say, this is about lowering the activation energy of the reactants, and therefore we have to use a catalyst. As you saw from those those microscopy images, the catalyst is sort of balls of often platinum, some sort of reactive metal for these reactions, spread on larger balls of carbon, okay? And actually what happens for, as I say, for all electrochemical reactions, what you have to have happen is the electron transfer, but also ionic transport as well to balance that reaction. And that's the same for the fuel cell reactions. So we have to be able to deliver our reactant to the surface, in this case hydrogen gas. We have to be able to split that hydrogen into protons and electrons on the surface of the catalyst. The electrons then have to be able to follow a conductive path out of the fuel cell. And the protons have to be able to follow an ionic pathway into the electrolyte and into the other side of the catalyst, and into the other side of the fuel cell. And so you actually have a thing called a triple phase boundary in fuel cells, that you're trying to maximize this area where you have electronic, ionic, and conductivity and gas delivery, i.e. reactant delivery to that surface as well. So we're always trying to increase the triple phase boundary to get as many reactions as possible happening per second and generate as much current as possible. You can also use a better catalyst, of course, for the same sort of engineering of that triple phase boundary. Unfortunately, it turns out that most catalysts that are good for the hydrogen oxidation and oxygen reduction reaction in fuel cells tend to be quite expensive metals. This is something called a volcano plot, which shows a sort of an ideal catalytic activity for different materials, and you can see things like platinum, palladium, iridium are quite high towards the top of this volcano, unfortunately. So a lot of research is into either reducing the amount of these metals that we use, or alloying them, or trying to use non-precious metal catalysts that have an acceptable performance as well. So this is a lot of focus of some of the research we do at UCL, and obviously many other groups around the world as well. Once you've got a good catalyst, you obviously want it to last for quite a long time, and actually they can degrade over time, although some of the degradation that occurs in fuel cells is perhaps a little less of an issue than in lithium-ion batteries, for example. But there are mechanisms by which the catalyst can degrade. So you can see on the left-hand side here lots of different ways that this could happen. You can have the platinum literally dissolving into the electrolyte. You can have the carbon corrosion occurring. Sometimes this is catalyzed by the platinum that sits on the carbon surface. That can introduce defects into your carbon, lower the conductivity of the carbon, and eventually actually just erode away the carbon so much that you don't have the same sort of structure there as well. There's also a process called Ostwald ripening, which is shown in this animation here, not for a fuel cell catalyst, but this is where metals end up agglomerating into larger agglomerates because of dissolving and redepositing over time. Obviously, you can have platinum particle detachment as well from the surface. When that detaches, it's no longer electrically connected, and therefore you lose one of those key components of all electrochemical reactions, that electrical contact between the electrode. There's a little video here showing some in situ TEM, some in situ microscopy of a platinum nickel alloy catalyst actually dissolving under different potentials. Okay, so fuel cells operate at relatively high voltages and in quite acidic environments in the case of PEM fuel cells, and these can be quite corrosive to a lot of metals. So not only are things like platinum, iridium, and palladium the best catalytic activity, but also they tend to be the most corrosion resistant in these cases as well. So we have to use these kind of materials, otherwise you get this dissolution of the nickel, as you saw in that video there. Okay, need to move on a little bit. So as I say, there's some ohmic losses as well, and also mass transport losses. These all combine to give this sort of overall picture of how the fuel cell voltage changes with current density. And we're trying to minimize all of these things. Okay. So one MEA, one fuel cell, gives you a voltage of, let's say, 0.7 volts when it's operating. That's not particularly useful, and so we have to stack these all together. And the way in which you stack lots of fuel cells together is quite difficult. You need good compression, you need good engineering to surround all of that. In an exploded view here of a stack, you can see there's lots of different elements. You might need cooling, water cooling, for example. You need to be able to deliver gases to all of these different fuel cell units independently, and you need to be able to remove water from the system quite well as well, and all the while having good compression to improve the electrical conductivity. So all of that comes together to give some quite good advantages of fuel cells. They're reasonably efficient, certainly more so than combustion-based technologies. There's no emissions at the point of operation. So if you generate your hydrogen with renewable electricity, for example, all you have is water coming out of the fuel cell, and you haven't even generated any emissions anywhere else either. A lot of hydrogen is actually generated from natural gas, so that does have emissions associated with it. But for example, for pollution issues in the centre of cities, then that's not an issue. They can be quite reliable potentially. So I've shown you that they're ostensibly quite simple, but actually that there's lots of scientific and engineering aspects to try and make these things work well over time. But potentially they could be highly reliable. They're very flexible in their design, okay? So the current you get out of it is proportional to the surface area of the fuel cell. So you can make a very small fuel cell for a portable application, or you can make a very large one to power a whole building or perhaps a small sort of community. And as long as you provide them with fuel, they have continuous operation, okay? So this is in contrast to batteries where all of the energy stored within a battery is sort of defined by the size of the battery, okay? So that means they don't really have charge times as such, so you just have to supply them with fuel. Some of the drawbacks are cost, so they're still very expensive. They haven't experienced the benefits of mass manufacturing that lithium-ion batteries have had in very recent years, and some of the material costs are quite high as well. And the infrastructure isn't quite there yet either. So if you want to fill up with hydrogen, there are a few stations dotted around London and elsewhere in the country, but there's not that same sort of infrastructure for fueling stations. Reliability is pretty good at the moment, but obviously something that needs to be improved a little bit as well. One of the key concerns that some people often have is safety, and this is going back to things like the Hindenburg disaster, which is a hydrogen-filled blimp that blew up. Actually wasn't really the fault of the hydrogen, a bit of a myth. But obviously safety is a big concern, and Toyota and other companies are working very hard to make sure that this isn't an issue. This is a short video from Toyota where they've actually shot their hydrogen tank with a bullet. You can see that there's no ignition when this happens, and actually, because hydrogen is a very light gas, it actually vents very quickly if you do get a catastrophic failure like this. These carbon fiber tanks in fuel cell cars are actually the strongest part of the car by far. So they've been tested in quite extreme environments. There's also a sort of a well-known test that was done by the DOE a few years back, which I think Alex referred to in his talk, whereby they simulated a rupture of a fuel cell tank in a vehicle and then set it on fire, and compared that to a gasoline to a petrol vehicle, and to see what would happen. As I say, hydrogen is very flammable, but it's very light as well, so it tends to flare in this sort of vertical flame. So you can see with the gasoline, because obviously it's a liquid, it sort of pools around the car, sets on fire, and has perhaps a potentially more disastrous fire there, okay? So it's not quite as simple as hydrogen is very explosive and therefore bad. Also, lithium-ion batteries suffer very rare but very well publicized failures as well. Paul probably talked a lot in detail about this, and there's some of his work shown here with other people from our group, looking at how batteries fail at very high time resolutions and with thermal imaging as well. So I should stress that all of these things are very rare and they're largely very safe technologies, but safety is definitely a concern that you have to think about. Just in summary is a bit of a difference, some of the differences between fuel cells and batteries. They're both electrochemical devices. A battery, normally a rechargeable battery, is a reversible one. So when it's discharging, it's operating as a fuel cell is in what's called a galvanic mode. But then you can switch that round and charge it to take it back to the other state. With a fuel cell, the reverse reaction is electrolysis of water, so splitting of water, as I talked about at the start of the lecture. That can be done. You can have reversible fuel cell electrolyzer systems, but it tends not to be the case. But fuel cells are open systems, and that means as long as you're supplying fuel, you can have power generated. Whereas, as I say, the battery needs to be recharged when it's empty. So there's no charging required in the fuel cell. However, often fuel cells will be hybridized with batteries in car systems and other systems, and that's because that makes everything a bit more efficient and actually means that the fuel cell can operate in a more continuous and more efficient manner than it can if it's going up and down with the demand of the energy. So a quick comparison between two fuel cell vehicles. I'm running a bit over time, so I'll probably leave it after this one. We've got a Toyota Mirai on the left and a Tesla Model 3 on the right. One of the main differences actually is in the weight of the sort of electrochemical unit, right? battery pack in this Tesla weighs nearly half a ton, whereas the fuel cell stack and hydrogen tanks are much less. However, the cars end up being about the same weight. So there's a lot of peripheral things that go around fuel cells that are required in the car. The energy storage is roughly similar, and in a fuel cell that just depends on how big or how pressure your tank is, whereas with batteries that's defined by the size of the battery pack. The charging time is the other main thing. So fuel cell cars can refuel very quickly in the order of minutes. Electric vehicles, it's more like half an hour. You can sometimes charge a bit quicker, but then when you do that, you actually damage the batteries quite a lot. So in order to have a long-lasting battery pack, you want to minimize that charge time, maximize that charge time, sorry. Fuel cell vehicles are normally hybridized with the battery, as I say. This particular Tesla vehicle doesn't have hybridization, but obviously in the future, hybridizing with things like supercapacitors is quite good. They have a similar sort of range. Fuel cells often have a larger range than some electric vehicles. The Tesla is particularly good in this respect, but the big thing is the cost of the fuel, as it were. So hydrogen is still quite expensive compared to electricity, which is very cheap. And charging if you slow charge a battery car, it's actually very efficient in charging as well. Whereas of course fuel cells are around 60 to 50% efficiency depending on how they operate. Currently the vehicle cost is a lot more as well. So this is actually one of the more expensive battery electric vehicles. You can get things for sort of roughly half this cost. Fuel cell vehicles are still very expensive, and actually a lot of them operate on leasing models. So you actually sort of loan the car in a long-term lease. Very quickly, I'll show some highlights of the research that we do at UCL into fuel cells. A lot of this is based around imaging, so thermal imaging on the bottom to see how the temperature distribution occurs in fuel cells. We look at X-ray imaging as well, so we can look at things like in situ compression of these MEAs. We can use it for modeling systems, and also something called neutron imaging, which is really sensitive to water, so we can see how the water is forming and gathering in these fuel cells. I'll skip over this slide where we do also do a lot of solid oxide fuel cells. There's quite a cool video here, which hopefully we can share later. But basically, we do some multi-scale modeling on these systems, and it's quite exciting stuff. I'll leave you on a couple of slides about how much fun it can be studying fuel cells at UCL. We have an outreach group called UCL, which has a fuel cell, which you can see here, and we take this to festivals and science events and power different events. So we were phone charging at Glastonbury. We power a music tent at a festival called Green Man in Wales, which is quite fun. So that's something you get involved in if you study fuel cells at UCL. And also just to leave you with this idea that it's a multidisciplinary problem, okay? So talked about some of the chemical engineering aspects around fuel cells, but there's obviously chemistry in there in terms of the materials, the polymers. There's a lot of physics involved. Obviously a lot of electrical engineering around the whole systems, and mechanical engineering if you're talking about a car as well. Something we haven't touched on is actually biological fuel cells as well. There's something called microbial fuel cells that uses microbes to generate electricity, which is quite interesting. So with that, I think I'll leave it there and open up to questions. Just to say that fuel cells are ostensibly simple devices that require lots and lots of intricate engineering and science in order to work well, and science and engineering from multiple different disciplines. Okay, so I think they're really exciting demonstration of modern chemical engineering, and something that is actually probably quite unique in the amount of electrochemical engineering that you will do in your fourth year in UCL if you choose to join us. Okay, great. So if you've got any questions, please put them in the Q&A section. I can see there are a couple there already, which I'll answer now. If you have any further follow-ups, then please do add them. So, okay, first question we had was from Elliot, saying, can the oxygen gas come from the atmosphere, or would it be better to have it pressurized like hydrogen? That's a really good point, actually. If I show you the next slide here, which is the Toyota Mirai, you can see there's some quite large grills at the front of the car. They're actually, as well as cooling the fuel cell, they are bringing oxygen from the air into the fuel cell. So most practical fuel cell systems will use oxygen from the air because it just simplifies everything. It means it cuts the number of tanks you have to have in half, and it just means that you can obviously draw you've got a free resource of oxygen in the air. The problem with that is you need to filter it often to get rid of particulates. One of the main problems is that oxygen is only 20% of air. Okay, so you get actually some electrochemical penalties compared to operating on pure oxygen. but the engineering and systems benefits that you get from that far outweigh that normally. So yeah, so most of them will use oxygen from the air. In the lab, sometimes we use pure oxygen in cylinders just to see what sort of benefits we can get from that, and because it might be easier. But yeah, largely oxygen from the air. Right, another question here from Anonymous. How developed is the use of microbes as the fuel? So yeah, that's something that's not particularly developed. It's quite a tricky thing to do. Obviously, you've got an extra aspect there of trying to keep some biology alive in your system rather than just you know, just the engineering aspects of these materials. They tend to be very low power and energy density, and so microbial fuel cells tend to be actually centered more around things like water purification. So the microbes aren't actually the fuel in that sense, they're more like the catalyst, okay? They are operating on a fuel which would be something like, for example, some sugars in water or any other sort of impurities in water as well. So they're very low power densities normally, and they have their own problems, but they're quite exciting in terms of water purification. I just clicked on the wrong question to answer there, which is the next one, which is it possible to use molecular sieves as proton exchange membrane? Interesting. I think it is possible as long as they can conduct protons. So some work recently has been quite interesting using graphene. They've shown that actually very thin layers of carbon graphene can conduct protons. But it's quite tricky to get. Basically, as I mentioned, you need a very good gas impermeable, I should say, layer in between these electrodes. And so if you've got any kind of gas leaking through these structures, it can be quite catastrophic to the performance. So actually, the use of one of these polymers is actually pretty good. And actually, Nafion has been well developed now for many decades and it operates quite well. So there are people looking into different systems of the electrolyte, but largely they based around polymer membranes. Okay, got lots of questions here. Let's just click off some of the other ones. How feasible is the reverse reaction, splitting water into hydrogen and oxygen to provide a continuous supply of reactants? Thank you very much. Okay, yeah, well, so it's very feasible. In fact, actually, if we want fuel cell vehicles to become ubiquitous, if we want what's called a hydrogen economy, then we need to generate hydrogen doing this, okay? We need to split water into hydrogen because that's much more sustainable than generating hydrogen from hydrocarbons such as methane, which is how most of it is done at the moment. The problem is that in the same way that fuel cells are only about 60% efficient, electrolyzers are only about 70–75% efficient, and they require electricity, of course, and so electricity is not cheap. However, if you use excess renewable energy, so often when it's very windy or at night time, for example, when the demand is lower, we actually have an excess of electricity sometimes, and power plants are often turned down or wind turbines are turned off so as not to affect the grid operations. So if you use that excess electricity to generate hydrogen, which can then be stored and transported elsewhere and used in a fuel cell to generate electricity, then that's a really good way of sort of effectively spreading out the electricity demand on the grid. It's not necessarily feasible to do that within a vehicle, for example. So you wouldn't have a vehicle filled up with water that then generates hydrogen and then generates electricity, because both of those processes are just causing inefficiency, okay? Then you would want to just have a battery electric vehicle, okay? Because they charge and discharge much more efficiently. The benefit is that the storage of the hydrogen is potentially easier than storing electricity in large batteries, and so moving towards this hydrogen economy is quite attractive. Where's the research heading now with fuel cells? That's a good question, a very broad question. As I showed on this slide here, there's lots of different aspects to fuel cells and fuel cell systems. So there's many different aspects of research. One of the ones around what I'm most interested in, I think, is about trying to reduce or remove platinum from the fuel cells. And actually, there's a lot of interesting work being done with non-platinum catalysts, and actually catalysts derived from carbon sources and actually biomass as well. So that's quite interesting. They're not quite performing as well as platinum at the moment, but they are obviously a lot cheaper and a lot more environmentally friendly. There's all sorts of research into understanding these reactions at a very fundamental level, understanding the performance of these polymers and improving those. And also, I mean, in UCL, we focus on lots of different aspects around things like water management and thermal management, things like compression, all of the sort of engineering factors that go into fuel cells to make them work well. So once you've got your MEA with your good catalyst and your good membrane in it, how do we then maximize the operation of that during the operating fuel cells? So there's lots of work that goes into that. So the short answer to that is actually it's everywhere. There's lots of fuel cell research going on, and in lots of different disciplines as well. Okay. Next question. Do you think it's feasible for farmers to use plant-based microbial fuel cells to generate electricity? As I said earlier, they tend to be very low powers at the moment. So in terms of generating useful electricity, it's not that promising. But what it is useful for is actually just, you know, for waste. So for waste that otherwise would be just disposed of, then if you can generate a little bit of electricity and crucially at the same time clear up that waste, so in the case of wastewater, for example, or sewage, then you can have a double benefit for microbial fuel cells. So that's quite cool. They won't be powering your car anytime soon, I'm afraid, or anything like that. What are the advantages of using direct methanol fuel cells, since one of the products is CO2? Yeah, good point. CO2 is a byproduct of that, so it's not as clean as hydrogen. Also, methanol is a much larger molecule than hydrogen. That means that actually the electrochemistry of splitting the methanol is much more complicated. And so when I talked about those activation losses that you get with hydrogen, the ones you get with methanol are actually very, very much bigger because it's a slow reaction. So in fuel cells, this oxygen reduction reaction tends to be much more slow than the hydrogen oxidation reaction. And so largely a lot of the research is actually focused on that oxygen side. When you look at methanol as a fuel, then you've got to look at both sides, and actually you've got to try and improve the anode and the cathode side in terms of the catalysis. There's also an issue because methanol is liquid. It can more easily transfer through the structure of the Nafion membrane along with the water. So you get this crossover issue as well, which can poison the other side of the fuel cell and also lower your operating voltage. The main benefit of methanol fuel cells and why they've received some attention is because of the fuel. The fuel volumetric density, because you've got a liquid, is much higher than gaseous hydrogen. It means you don't have to have high pressure tanks. It also means it's much easier to transport liquid fuels. We know how to do that with petrol and things like that, whereas hydrogen is actually very difficult to contain for long periods of time. So that's the main benefit of methanol fuel cells, but it's probably not going to take off for automotive. Right, what else have we got here? Is it possible for biocatalysts to be used to increase fuel cells efficiency? Yeah, so in terms of microbial fuel cells, that is a biocatalyst. Yeah, the microbes themselves are the catalyst, and also, as I say, you can make catalysts from biomass waste. So by carbonizing biomass to produce these interesting carbon structures. Try and get through the rest of these now. What time are we on? We're just coming up towards 11. So more stuff about microbes. Perhaps I should have put a bit more information about microbial fuel cells. I should stress that actually that they're a smaller area of research compared to PEM fuel cells, but they are quite interesting. How significant is the role of biogas in that context? I'm not entirely sure what you mean by that, but I guess gas generated by biodigestion and things like that. Normally, you would probably try and use that gas for other things like combustion, but you could in theory use that in a fuel cell as well. What else have we got here? Is there any environmental restriction with fuel cells? That's an interesting question. I think that the recycling of fuel cells, because you have small amounts of platinum in them, would have some sort of restrictions. You don't necessarily want to lose platinum to the environment, but it's fairly inert, so it's not too much of an issue compared to lithium-ion batteries. Actually, a lot of which contain cobalt and metals like that. They are in theory much more recyclable, much more easily recyclable. And also, in theory, they shouldn't cause as many environmental problems. Perhaps some of the polymers used in the electrolytes they can release hydrogen fluoride gas sometimes, but in very, very small amounts. So there's not really so many environmental issues. It's more around the safety of the high pressure hydrogen, I guess, that's the issue there with fuel cells. Yeah. Can the oxygen gas come from the atmosphere? Done that one. And the final one at the moment, methanol fuel cells were found to cause blindness in mice when tested. Why is this? Right. Well, that's obviously an issue. Methanol does cause blindness in mammals compared to ethanol, for example. If you drink methanol, you will go blind, unfortunately. I don't know the exact biological mechanism of that, but it is a bit of a concern. Methanol fuel cells probably experienced much more interest about 20 years ago, as I say, largely because of the energy density of the fuel there. But some of the issues with the efficiency of them and the crossover and things like that have been largely insurmountable, and actually so PEM fuel cells, hydrogen-based fuel cells, have been the ones that have sort of won out there in terms of having good useful applications. Okay. I skipped over them in the interest of time, but just to give you an idea that there are actually fuel cells out there operating today. So the Toyota Mirai we've mentioned a few times, we actually have a couple of these at UCL. Our group uses these to go off to experiments and to drive around and promote fuel cells. And there's a picture of some of our PhD students there, Jen, Zara and Rob, looking at the Toyota Mirai. There are other fuel cell vehicles as well. I think the Mirai currently is the only one you can own outright. A lot of them have other lease options, but that's changing all the time. So Honda, Hyundai, etc. have these fuel cell vehicles as well. Obviously not as ubiquitous as battery electric vehicles. As I say, a lot of that is because of the cost of batteries going down so drastically recently, which is great. However, fuel cells probably have a real niche in larger vehicles. It's much more difficult because of the weight of the batteries. Much more difficult to power large vehicles. So Elon Musk could tell you that he could power an 18-wheel truck. But actually, I think the consensus is that fuel cells will really need to step into much larger vehicles. And currently in London, there are a few buses, the RV1, the RV2, I think, that are fuel cell buses operating in the city. So we do have fuel cells around us already, and much less so than battery electric vehicles. So finally, I'd like to highlight an example from UCL. This is a spin-out company from UCL. And this is called the flexible fuel cell by Bramble Energy, and it's flexible in design because it uses printed circuit boards, which are very cheap and mass manufactured. It uses these as the current collectors and as the sort of external components around this membrane electrode assembly that we talked about at the start of the lecture. So that's quite exciting. They still work with us in the labs quite a lot, but they're doing some really interesting stuff and about to take off, I think. So there's quite a few jobs coming up in fuel cells, hopefully, with them and with other companies. As I say, it's a multidisciplinary problem, and so not only some of the things you learn in chemical engineering, but if you've got other backgrounds and interests as well, there's always a job for you in fuel cells and in batteries, to be fair as well. So I think electrochemical technologies are really exciting, and we give a sort of a pretty in-depth view of these things in the curriculum at UCL, and I think it's quite unique actually. So if you're interested in sort of newer aspects of chemical engineering, less traditional aspects such as electrochemical engineering, then I think it's a really good choice for you to come. We've had one more question just come in, which I'll leave as the last one. How do we increase the efficiency of fuel cells? So this comes back to this polarization curve concept that I talked about here. So there's lots of different ways to increase the efficiency. There's an inherent maximum efficiency that you can't get around, but basically what we're trying to do is make this curve be higher, okay, at higher current density. So this means using better catalysts that are more reactive to the reaction, thinner, more conductive membranes, more conductive components in the gas diffusion layers, all of these sorts of things. So that's how we increase the efficiency of fuel cells. But there's a fundamental sort of thermodynamic efficiency issue, and as soon as we start to draw current off them, then the efficiency decreases. But it's about minimizing that decrease. Okay. I'm not sure about access to the slides. I'm quite happy to provide access. I don't know. I'll follow up with Mark about how best to do that. There's a lot more information on our website as well, the Electrochemical Innovation Lab website, the EIL. And I'm happy to take questions via email after this as well. Hopefully it's been a useful overview of what sort of stuff you'll learn about at UCL, and if you continue on to do research, for example, we offer research programs in the master's programs and obviously PhDs as well. and we do a lot of work around fuel cells and batteries. So if that's something that interests you, then I think UCL is a great place to study chemical engineering. Thank you very much for your attention, and yeah, hopefully see you at UCL next year. Bye.